And let's give it a try. Okie doke, predict the major products for each of the following reactions. Let's see here. You notice that both of them have a ketone or an aldehyde, and you see magnesium bromide. So these are Grignard reactions. So this is some practice on Grignard chemistry, which we looked at in the alcohols chapter. Well, in the first one, we have ethyl magnesium bromide. You could write out the Lewis structure, or the partially condensed structure, I guess, like this. Here's our ethyl carbanion. It's going to do a nucleophilic attack at our carbonyl. It's going to end up forming this intermediate. This, where we have this alkoxide, and now we've got the initial ethyl group, but we have a second ethyl group like this. So that's what we get after the first step. And then we're going to treat that with water in the second step, or sorry, they put, water, which is going to behave as an acid. And that's going to give us our final product, which would be this. So let's draw that out. So we end up with a tertiary alcohol in the first one. The second one, we have benzaldehyde. Same thing, we're treating with phenyl magnesium bromide this time. So let's draw out the phenyl Grignard. It's going to act as a nucleophile. Our carbonyl acts as an electrophile, and we form this intermediate, which is going to look like this. Remember, I use pH as my abbreviation for the aromatic ring, and I've got two of them here. And then after treating that with water, water acts as a proton donor, and I'm going to end up with another tertiary alcohol. So it's going to look something like this. It's going to be this compound is what I end up with. So so this is benzyl alcohol. So sorry, no, it's this compound that you end up with. This is the same as this. So that's the compound you end up with in that reaction. So a little bit of practice on Grignard chemistry. Remember, one of the nuances is that in our textbook, in the older versions, it says water for the second step of the Grignard. You could also put H3O+, that works too. Either one is totally fine. Let's move on to the next one, which deals with more Grignard chemistry in a way, because we're trying to make some new carbon-carbon bonds here. And in the first one, we're starting it with a secondary alcohol, and we have 5 carbons overall, but then we have 6 carbons here. And if you think about how would you make this tertiary alcohol, well, I think the best way to make this would be if we had the ketone, right? If you had this ketone, cyclopentanone, all you'd have to do is treat that with methyl magnesium bromide in the first step, followed by treatment with aqueous acid or water in the second step, and that would give you this tertiary alcohol. So then the question becomes, well, how do I go from the alcohol to a ketone? Does anybody have a suggestion? How to get from the secondary alcohol to the ketone? Well, Lindsay, I think you said PCC?
Yeah.
Perfect. Sounds good to me. I like PCCs too. Let's do it. So we'll put that down. We can even write this all in one step. I know you guys follow me. So first step, we'll put PCC. Second step, we'll put methyl magnesium bromide. And the third step, we'll put H2O or H3O+, like that. And that is going to give us, you'd call that what, 1-methyl cyclopentanol? Okay. And there's no chiral centers in there to worry about. The next one, I would say same vein, except instead of a ketone, you're going to start with an aldehyde, right? So in terms of retrosynthesis, you're starting it with 7 carbons here, and then you end up with 8 carbons. You want to add this carbon here on the end. And so if we had this aldehyde, this would be cyclohexane carbaldehyde. If we had that, we could do the same thing. We could just take that and treat it with methyl magnesium bromide and then add a proton source. And so we could actually use the exact same reaction conditions we did for the first one. Why don't we pick a different method of oxidizing the primary alcohol to oxidizing the primary alcohol to a aldehyde instead of PCC? Does anybody have another one that we could use? Another favorite? There's
Sodium
two.
dichromate, sulfuric acid, and water.
Uh, that will oxidize the primary alcohol. So if you used, let's see here. There we go. If you use sodium dichromate, sulfuric acid, and water, since this is a primary alcohol, then you'd end up with the carboxylic acid. So it oxidizes it all the way. It goes through the aldehyde, but then it gives you the carboxylic acid. So we need a more mild method. Another method that you could use would be the Des-Martin reagent, the DMP, the Des-Martin perodenane, or the Swern reaction. Either one works. Let's do the Swern reaction. So the Swern reaction is a two-step reaction. The first step is that you treat the compound with dimethyl sulfoxide and oxalochloride, so COCl2. That second step is you treat it with triethylamine. That would give you the aldehyde. Then you would treat it in the third step with methyl magnesium bromide. And then in the fourth step, you treat it with water or aqueous acid. And that would give you the secondary alcohol which you desire. There you have it. So a little more practice using some Greenyard chemistry. And, also involved some oxidation. So I'd say this one kind of involves oxidation and Greenyard. Go ahead. Somebody have a question? Okay, I thought I heard a question. All right, let's try this one here. So the next one, we have KCN and HCl. And so KCN and HCl is used to form a cyanohydrin. Remember, if you have carbonyl compound and you treat it with KCN and HCl together, you end up with this, where you have like an alcohol and a nitrile together, and we call that a cyanohydrin. So what we're going to get from the first step will be the cyanohydrin. Let's draw that out. It's going to look like this, where we have our alcohol, we have our nitrile over here. We also have a hydrogen here. Pencil that in like this. So this is our cyanohydrin. And we learned two reactions with the cyanohydrins. We said you can reduce this to an amine using lithium aluminum hydride. But if you treat it with an aqueous acid and heat it up, it converts this into a carboxylic acid. So let's write out what the product would look like after the second step. Or, oops, that's not very pretty. We're going to end up with this, where we have the carboxyl group here, and we still have the hydroxyl group on here, like this. So a little practice of cyanohydrins and what we can do with a cyanohydrin. Let's see, what's next? Oh, more cyanohydrin chemistry. Right, the only way that we know how to make a compound that has an alcohol and a carboxyl group coming off of it is to proceed through a cyanohydrin. So that means our retrosynthesis is, oops, I didn't mean to put the ruler on there. Our retrosynthesis is going to look something like this. We need to have cyclopentanone, and then we would make a cyanohydrin from that. And so we could take this and we could make a cyanohydrin, right, like this. And then all we have to do is treat that with aqueous acid and heat it up. So then the question becomes, well, how do I go from here to here? I'm not going to spend a lot of time on that because we've looked at so many ways to oxidize an alcohol. So let's just pencil it in here. I'll start over here maybe in red ink. So we'll start with our alcohol, and we're going to oxidize that to a ketone. For that, we can use sodium dichromate, can't we? So let's try that. Sodium dichromate, sulfuric acid, water. That's going to give us cyclopentanone. And then if we want to make a cyanohydrin, we treat that with KCN and HCl. And that gives us a new carbon-carbon bond, which is pretty cool. Like this, KCN and HCl, like that. And then if we want to make the carboxylic acid, carboxyl group, I'm just going to delete this. What are we going to do? We're going to take this and we're going to treat that with H3O plus and heat it up. And that's going to convert the nitrile into a carboxylic acid. Whereas if we wanted to take the cyanohydrin and we wanted to make a primary amine, that's 2 steps. The first step is lithium aluminum hydride, and the second step is going to be to treat it with water. All right, there we go. So that's that one, a little practice with cyanohydrins. They seem to be really real favorite of the author of the book. Anyhow, let's move on from cyanohydrins and let's try some Wittig chemistry, right? Here we see a Wittig reagent. So this would be an ylene that you see here. And you could draw the ylid form of it. You could draw the other resonance contributor, which I think is even easier to use in your mechanism. So that's going to look like this, where you have pH3, got a positive charge here, and then you've got a negative charge on this carbon. I'm kind of running out of space here, but the idea is that this is a carbanion right here, and we can redraw that in a second. But there we go. So that's going to react with the carbonyl. Now first, let me show you the simplest possible way of doing this. Are you ready? So I'm going to erase what I've got here so far. Here's the easiest way to kind of connect the dots. The bond that you're going to form, right? You're starting with a ketone. You're starting with a ketone in a Wittig reagent, so you're going to make an alkene. Okay, what's that alkene going to look like? Here it is. Here's how you connect the dots. Remember, in the end, the phosphorus with the triphenylphosphine, the phosphorus with the 3 phenyl groups is going to be attached to the oxygen, right? Everything I have highlighted in yellow is going to give you triphenylphosphine oxide. So pH, 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 right? That comes from everything that's in the yellow highlighter. So where do the bonds connect? It's going to be between this carbon that I'm highlighting in green and this carbon that I'm highlighting in green. So all you've got to do is draw the double bond, but instead of the double bond being to an oxygen, now you just remove that, it's gone, and it's going to be to all of this. So you've got CH, CH2, CH3. So CH, CH2, CH3, done. There's no E or Z to worry about here. Normally, in this case, you'd end up with a Z alkene, but you don't have to worry about stereoselectivity in this case because you have 2 ethyl groups here, so there's no E or Z. Now, if you wanted to practice the mechanism for this reaction, what you want to do is draw the carbonyl. I'm just going to change the conformation of the compound a little bit, like this, and then you want to draw your ylid like this. We have 1, 2, like that. Okay, so this is my ylid. This is the exact same thing. What I have here in this black circle is the same thing as this. Okay, I just took this bond and moved these electrons up here, and I'm kind of putting it in an orientation that's easy for me to draw the mechanism. So the first step is a 2+2 cycloaddition. This is my nucleophile, that's my electrophile. I've got a pair of electrons on the oxygen here, and what happens is a pair of electrons from the pi bond makes a bond between the oxygen and the phosphorus. That produces the oxaphosphatane. All right, so let's draw the oxaphosphatane. It's a 4-membered ring that's got a phosphorus and an oxygen in it. On this carbon, we've got 2 ethyl groups like this. On this one, we've got this ethyl group over here, and then you still have the or the pH3. You've got 3 phenyl groups coming off of there. So now we do the fragmentation. What's the mechanism of the fragmentation? I'm going to form a double bond between the oxygen and the phosphorus, and my alkene is going to be formed like this. So I end up with, let's draw this out like this. So triphenylphosphine oxide, and what's my alkene look like? I've got a double bond, I've got an ethyl group on here, and I've got 1 ethyl group here and 1 ethyl group here. What I've drawn here is the exact same product that I drew on the other slide. I've just got it twisted another way, right? On the other slide, I had it drawn like this. Okay, but these 2 things are identical. They are the same as. Give me a thumbs up if you follow me on the mechanism. The Wittig reaction. This is the Wittig mechanism. And students need to know the Wittig mechanism, the formation of the oxyphosphatane, and then the fragmentation to give us our alkene. And again, in this case, there's no E or Z to worry about. So it makes it a little bit simpler. I'm not going to go over the mechanism for the Horner-Wadsworth-Emmons reaction. It's virtually identical. The only thing that we have to remember here is that we end up with the E product. So with Horner, so this is the Horner-Wadsworth-Emmons reaction. We'll put here E product is what's going to predominate. So here's how we're going to do it. The double bond that's formed is going to be between the carbon of the carbonyl, this carbon, and this carbon, the carbanion from my Horner-Wadsworth-Emmons reagent. So this is what the product will look like. We're going to have our methyl group. Then we have the first carbon that I have highlighted in green, our double bond, our hydrogen. And since it's an E product, my ester is going to be over here like this. And so that will be the product. And of course, I have a hydrogen over here. All the rest of this here, that ends up in the side product. Okay, don't even worry about the side product. I'm never going to ask you to draw what the side product of the reaction is. Okay, and that's it. So we end up with the E product. So E product. There we go. So Horner-Wadsworth-Emmons reaction. Try one more problem before we get into something new. It says identify the reagents that you would use to prepare each of these compounds by a Wittig reaction. Well, let's do a little retrosynthesis on A. Going backwards, there's two possibilities, isn't there? So we'll use a red arrow and a blue arrow. If I was to use the blue arrow, I'll draw the two possible ketones. So one ketone that I could have would be this, which is butanone. And then in that case, my Grignard reagent would be from these three carbons. So then I would have my triphenylphosphine. So go pH3, I've got my phosphorus, and that's going to have a double bond. So then I've got 1, 2, 3 carbons like that. So that's one possibility, is this one here. And the other possibility would be what? Would be if I had this is my ketone. So what I'm going to draw, so it's not a ketone, it would be an aldehyde. There we go. So this would be my aldehyde. And then my Grignard, my Wittig reagent would be this, BPH3. So the question is then, would I want to make the Wittig reagent the one in blue or the one in red? Which one would be the one that would be easier to make via an SN2 reaction? The one in blue or the one in red?
Blue.
Absolutely, 100% right. Right? Because if you wanted to make the one in red, Lindsay, you'd have some serious issues, wouldn't you? Because then you'd have a secondary alkyl halide. I'll just put X, okay, plus triphenylphosphine. That's going to not be very good for an SN2. Whereas if you had the blue one, then you've got 1, 2, 3. You've got, 1 bromopropane plus triphenylphosphine. Nothing wrong with that. BPH3. I mean, that's going to do an SN2 like nobody's business. So this would be the correct route. So what's that going to look like when you put it all together? Well, what it would look like is, something like this. So I would start out with, and we're just doing A. I don't know where I went there. Please just tell me that didn't get deleted. Good. So we're doing A. So I would start with propyl bromide, 1 bromopropane or 1 iodopropane or 1 chloropropane. In the first step, I'm going to treat that with triphenylphosphine. In the second step, I'm going to treat it with butyllithium. That's going to give me my Grignard. Why do I keep saying that? That's going to give me my Wittig reagent, which looks like this. This is the ylene form. I prefer to draw the ylide form, which is this, where you show the negative charge here and the positive charge here. And then we're going to treat that with the appropriate ketone, which we said was this one, which is butanone. And then that's going to give us our product. Nothing more than that. So where the heck am I? So that's just going to give us this compound. So we have, this. Then we have our double bond. This, and then 1, 2, 3. There we go. like that. So that gives us our final product. Okay, so that's the whole sequence for A. I'm going to have to switch over to a blank document to solve B. So let's do that. And so this is the thing is with this one is that there's a plane of symmetry down this molecule, right? I hope you can see that there's an axis of symmetry here. And so there's only one way to make this compound anyway, right? We're going to break the bond here. And so in terms of our retrosynthesis, we're going to need this compound, which is benzaldehyde, and then our alkyl halide would be this, which is benzyl bromide. That's what we need to do this Wittig reaction. So what's it going to look like when we put it all together? We're going to start with benzyl bromide, which is PHBr, right? This is the same thing as this. I've told you many times that this is a great lacrimator, makes everybody cry. So this compound, first step, triphenylphosphine. Second step, butyllithium. That gives us our Wittig reagent, which is going to look like this. So we have our carbon here, then we have our phosphorus here, like that. So there's our Wittig reagent, and then we're going to treat that with benzaldehyde, which is this compound, and we're going to end up with this product. So let's draw it in here, and there you have it. And notice that you end up with the E alkene. Well, why would that be? It's because this is resonance stabilized, right? You should be able to draw all the resonance contributors, PPH3. So you should be able to draw all the resonance contributors to this to show the delocalization of these electrons. You would start, like this and say, okay, well, I can draw a resonance contributor like that and push the electrons all the way around the ring. And that is why I end up with the E product. There we go. Some good practice on Wittig, Grignard, cyanohydrins, a little bit of everything. And that brings us to the very last reaction in the entire chapter, which is down here. So we've covered Wittig, we covered Horner-Wadsworth-Emmons, and now we're on to the very last question, or very last section rather, which is 19.11, which deals with the Baeyer-Villiger oxidation. And this was discovered partly by Bayer, the same Bayer that started the Bayer Pharmaceutical Company, which is around today. So he did a lot of stuff, even some pretty cool chemistry, and he discovered a reaction called the Baeyer-Villiger oxidation. And if you remember earlier on, especially in the alcohols chapter, I remember mentioning this to you. It was only a couple of weeks ago. I said, well, if you take a secondary alcohol like this, let's say you take this secondary alcohol and then you oxidize it, right? I said you oxidize it to a ketone and it can't be oxidized any further. And then I said, well, there are exceptions to that, and this would be the exception. So you can oxidize a ketone further if you use a peroxy acid. You can insert an oxygen in between the carbonyl carbon and one of the R groups. And it's a pretty cool mechanism that involves what's called a migration. It says here an aldehyde or a ketone is converted into a carboxylic acid or an ester, respectively. So let's check out this mechanism. I will not ask this mechanism, but it is very cool and it's not very long. So check it out. You have your peroxy acid here. This is peroxyacetic acid. The last oxygen, the one closest to the hydrogen, that acts as a nucleophile, and it forms this intermediate that undergoes a proton transfer. And then you have this rearrangement here. But notice the rearrangement. If we zoom in on it here, look at the arrows. You get this first arrow here to reform the double bond, I should say. But check out this. This is kind of the key step. Is this R group here? The pair of electrons here are moving over onto this oxygen like this. And so that is called a migration of the alkyl group. So it's moving over, and then you end up forming acetic acid as a byproduct in this case. So this is acetic acid that's formed over there. So you end up starting out with this ketone, and you end up with an ester. So this is the first way that we've learned to make an ester. We will look at other ways later on. Yeah. Another thing that I'll tell you is this thing here. This is called the Kriege intermediate. So the Kriege intermediate. Anyhow, it's not in our textbook, but it's something that you might want to look up just for fun if you're interested in it. Anyhow, you know, if you're thinking, okay, cool, if I have a symmetrical ketone or aldehyde, no problem. I just insert an oxygen on either side and I get the question right. So let's say you had cyclopentanone. When you insert an oxygen in there, if you have a cyclic ester, a cyclic ester is called a lactone. It's got a specific name, so a lactone. I want you to remember lactone. It comes up quite a bit in the class. A cyclic ester is a lactone. What was my point here? Is that if you have an unsymmetrical ketone or aldehyde, you know, how do you know which side the oxygen goes on? Well, it's based off of something called the migratory aptitude of the group. And the factors that contribute or control the migratory aptitude of the groups are actually not completely understood. But what we do know is that the rate of migration is like this. If you have an aldehyde, you're going to end up with a carboxylic acid. After that, the tertiary group's going to move first, then the secondary tied with phenyl, then a primary, then a methyl. And I know that somebody's probably thinking, well, are you going to ask me secondary and methyl? Of course not. It's not my job to try to confuse you. It's just the migratory aptitude that we need to know. So we use this trend to determine, you know, where the oxygen is going to go. What's the regioselectivity? If you look at these two examples here, we see that this carbon here, look at this carbon here, it's attached to, you know, 3 hydrogens, whereas this carbon is attached to 2 carbons going out from my carbonyl. So I have a methyl group versus this secondary carbon. So which one's going to migrate first? Well, it's definitely not going to be the methyl, and that's why the oxygen is going to insert on this side, and we end up with this ester over here. So that would be called isopropyl acetate, that compound. And the next one, if we have an aldehyde, if you ever have an aldehyde, you always end up with a carboxylic acid. So that's how the migratory aptitude works. And I would say you should memorize the migratory aptitude. So memorize this for the quiz and at least have a working knowledge of it for the final exam, I would say. So let's take a look at some examples here. It says predict the major product for each of these reactions. We're taking a ketone and an aldehyde and treating them with a peroxy acid. So this is a Baeyer-Villiger reaction. If we look at this carbon over here, it's attached to only 1 carbon going away from the carbonyl. So this is like a primary carbon, whereas the one on the left is attached to 2. And so it is secondary. What was the migratory aptitude? It was a hydrogen followed by tertiary, followed by secondary and phenyl, followed by primary, followed by a primary, followed by a methyl. And so, because of that, it's going to migrate on the second, this side is going to have the greater migratory aptitude. And thus, our final product is going to look something like this, where we have our ethyl group over here, we have our oxygen, and then we're going to have our cyclohexyl group, like that. So that would be called cyclohexylpropanoate or cyclohexylpropionate, either one. Totally fine. In the last one, of course, we have a proton, and that has a higher migratory aptitude than anything, especially compared to this secondary carbon over here. And so we're going to end up with a carboxylic acid that's going to look like this. Baeyer-Villiger reaction. Now you've learned all the reactions of chapter 19, so let's take a look at some synthesis strategies. And we've learned 3 different ways, or not 3 new ways, but 2 new ways and 1 old way, the Grignard. We've discussed 3 ways to make new carbon-carbon bonds, starting with an aldehyde or a ketone. We can use a Grignard, or a cyanohydrin, or a Wittig reaction. And so if we want to add carbons, we might want to consider the three of these. You should be able to make a list of products that can be made from aldehydes and ketones. So make sure you're fully aware of all of the different reactions that we used. And if you go down to the very end, I've gone over this table with you a few times. So now we've covered everything officially. We covered Greenyards, and we covered reduction. We covered Rainy Nickel. We covered Wolff-Kishner. Everything has been covered. If we go back here into the synthesis section, we have some really neat problems that ask us to propose some syntheses for these transformations right here. Well, in C, we're starting out with a compound that has, this compound has 7 carbons in it, and we're ending up with a compound that has 8 carbons in it. So we want to add a methyl group and a hydroxyl. You know, what I'm thinking about here is, what if we had this compound, right? If we had this compound, so 2-methyl cyclohexanone, then all we would have to do is take that and treat it with methyl magnesium bromide in the first step, followed by H2O or H3O plus in the second step, and that would give us our product. So then the question becomes, well, how do I get from here to here? How do I get from here to here? Well, something else I remember is that if I'm starting out with an alkane, the only possible reaction that I can do is a bromination, right? A free radical bromination, and I can install a bromine at this position. Well, if I can install a bromine at that position, I can do an elimination to form this alkene. If I can form that alkene, I can do an anti-Markovnikov addition to produce this alcohol. If I can produce that alcohol, I can do an oxidation to make this carbonyl compound. And that is the rationale we want to take for a problem like this one. So let me go over to a blank document, and we'll walk through the whole thing step by step. Just bear with me here for 1 second. And let's take a look. So this is there we go. So we're starting with methyl cyclohexane, and we want to make this 1,2-dimethyl cyclohexanol, this compound. So what's the only thing that we can do at first is to treat it with bromine in light or bromine in heat, and that gives us 1-bromo, 1-methyl cyclopropane. And then if we treat that with a non-hindered base, that's going to give us the Zaitsev product. So we'll treat that with a base like sodium ethoxide or sodium methoxide. It doesn't matter. And then we're going to get the E2 product, namely the Zaitsev product. So this is our Zaitsev alkene, as opposed to the Hoffman, which would be this one. We don't want the Hoffman alkene. And so now to put the hydroxyl onto this carbon, I'm going to do an anti-Markovnikov addition of water. So I'm going to use borane and THF, followed by hydrogen peroxide and sodium hydroxide. That gives me this compound. And now we need to oxidize that to a ketone. There's so many things we could use, but let's just use PCC. We'll even put a solvent, dichloromethane. There we go. So that gives us 2-methyl cyclopentanone. Now, to get to the final product, all we need to do is treat it first with the methyl magnesium bromide as our nucleophile. And then in the second step, we're just going to use aqueous acid or water to protonate. And there you have it, my friends. But how many total steps is that? That's 1, 2, 3, 4, 5, 6, 7. 7 steps to get to the final product. It's certainly a number of steps to get there. But again, you've just got to know all of the reactions frontwards and backwards. That will definitely get you to your final product here. Let's try 19.40D. So 19.40D. In this one, we're taking same starting material, and now we want to make this compound. Here, where am I missing? this. So we're starting out with 7 carbons, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 7 carbons to 9 carbons. Well, you can see that we're going from a ring to a linear compound, and so we have to break the ring open somehow, which tells me that I want to end up making, I want to somehow end up making this compound, because if I make that compound, then I can break it apart to give me 1, 2, 3, 4, 5, 6, 7. I can break it apart like this, right, using ozonolysis, and that'll give me this compound. I've still only got 7 carbons, but you can see that this aldehyde will undergo nucleophilic attack with methyl magnesium bromide, and this ketone could undergo nucleophilic attack with methyl magnesium bromide. Now you might be saying, well, that would give you 2 alcohols. It would, but on this side you'd get a secondary alcohol, and on this side you get a tertiary. So then if you try to oxidize it to a ketone or an aldehyde, the only one that's going to oxidize is the secondary alcohol. The other one's not going to oxidize at all. So then the question becomes, well, how do I get from here to here? Well, good news is we just did that in the last problem. So let's back up a little bit here. Let me just erase some of this, and we'll write down the first few steps. So delete, I'm going to delete these as well. So our first steps, just repeat of what we did in the last question. So bromine and light. And why don't we do both of these steps? So second step is sodium ethoxide, and that gives us 1-methyl cyclohexene. Then we're going to treat that with ozone. So 1 is ozone, 2 is DMS, and then we end up with 1, 2, 3, 4, 5, 6, 7. So we have a ketone on this end and an aldehyde on this end. Now, if we treat that with a whole bunch of Grignard, so we'll put excess methyl magnesium bromide. I got ahead of myself there. Excess methyl magnesium bromide, followed by aqueous acid or water. Then we're going to do the nucleophilic attack at this carbon and this carbon. I still see my screen. Okay. And we're going to do the nucleophilic attack at both of those carbons. So what's that going to give us? Well, what we're going to end up with is something that looks like this. So we have 1, 2, 3, 4, 5, 6, 7. But now here, we're going to have this tertiary alcohol, and here we're going to have this secondary alcohol. Now we've got 9 carbons in the molecule. And so if you try to oxidize both of those, since this is tertiary, it's not going to oxidize, but this is secondary, so it will. So we'll just treat it with PCC, and that gives us the final product. Excuse me. Another one of those reactions or another one of those syntheses where you really need to be aware of all of your reactions in order to get to the end. Let's try one more. This one is 19.40E. 19.40E. And now we're making an imine. So we're starting out with this compound. This is called methylene cyclohexane. And then we're making this imine. We can definitely do a retrosynthesis on an imine. We just did it. All right, so what would we form the imine from? We would form it from this compound, so cyclohexane carbaldehyde, and this is called isopropylamine. We haven't done amine nomenclature yet, but this makes it a little bit simpler. We need to get from here to here. And so what we're going to need to do is an anti-Markovnikov addition of water, and then to oxidize that primary alcohol to an aldehyde. So let's do that. So first thing is an anti-Markovnikov addition of water, BH3 and THF, followed by hydrogen peroxide, sodium hydroxide. That will give us this compound. Then let's just oxidize it. Let's try desmartin periodinane for a change, which is this, gives us our aldehyde. And then to make the imine, we're going to treat it with this amine, a catalytic amount of acid, and we're going to remove water, and that gives us the imine. There we go. So a little bit of practice on some problems. Section 19.13, we could just go over that very quickly because we would have covered all of these concepts in Organic Chemistry 1 about spectroscopy. So a couple things that you should remember is if you're talking about wave number, we saw that wave number was equal to 1 over 2 times pi times the speed of light divided by F, which is the bond strength or the force constant over the reduced mass and the square root of those. So what happens is if we reduce the bond strength by having a conjugated bond, well, since bond strength is directly related to wave number, and this is actually wave number, not frequency. Anyhow, we're going to have a lower absorption when we have conjugation. Also, ring strain is going to increase the wave number. We don't go over the reason why that is in the class, but that's something that you might want to be aware of. Another thing is the aldehydic CH stretching. You see two signals. They're usually around 2750, 2850. It says here between 27 and 2800, roughly, I would say. Those are usually pretty easy to spot. You can see them here very clearly. If you draw a line at, come on, ruler, there we go. If we draw a line here like this, okay, at 3000, you can see we have the aldehydic stretching here and here. So that's usually a dead giveaway that you've got an aldehyde, and obviously you can see the carbonyl stretching here as well in the IR. What else? We know that protons that are neighboring a carbonyl are going to be deshielded by that carbonyl. And if you have protons that are alpha to a ketone, for example, they're deshielded by about 1, or they cause a shift of 1 part per million. Roughly, aldehydic protons are the only ones that we see that come up around 9 or 10. They're usually not split. We sometimes see exceptions to that, but not a whole lot. Carbonyls always show up around 200 parts per million. And that's everything for spectroscopy. And these are all the reactions in the book that we need to know for this chapter. So, I think I've brought this up in class before, but sometimes students will ask me, oh, is there a place where I could find a summary of all the reactions? First of all, I would recommend writing that down yourself. Try to write down, okay, every single reaction in every chapter that you look at. And keep in mind that for your quizzes, you're always allowed to bring in the reagent sheets that I have posted in the chapter modules. I usually post them in the quiz announcement too. You're not allowed to write anything on those, but you're allowed to bring them into the quiz. And yeah, also at the end of every chapter, he always has a summary of all the different reactions that were covered in every chapter. So you want to work on those as much as possible.